Hello and welcome back. So we'll continue with the past year of 2019, section D. Question 16, we have two long parallel wire P and Q separated by a distance 15 millimeter carrying currents of 5 ampere and 2 ampere respectively. So calculate the resultant magnetic field along the midway points between P and Q. So in that chapter, we have learned how to derive magnetic field using Ampere's law and the magnetic field produced by a long straight conductor wire. So it is given as mu naught I over 2 pi r. So you can revise back how you do the derivations. It's quite simple. So we will straight away use formula for our discussion here. So magnetic field is a vector quantity. So before do the calculation, you need to identify the direction first. Okay. So the magnetic field, okay, direction can be identified using the right-hand grid rule. So for example, for wire P, so your thumbs pointing outward. So you can find out that the magnetic field in the middle between P and Q is into the page. And as for the wire Q, you apply right hand and you can also obtain that the direction is also the same. So we can see the magnetic field in the middle between P and Q is in the same direction. So we can just do summation for the B by wire P and also the B by wire Q. Okay, they are in the same direction. So apply the formula, we have mu naught over 2 pi. Okay, multiply the current. Current of P is 5 divided by the distance, which is half of 15 millimeter, 7.5 millimeter. And as for wire Q, it is 2 ampere over 7.5 millimeter. Okay, straightforward. So do the addition and also the multiplication. So it will be mu naught shift constant 33 divided by 2 pi. Okay, times same denominator, so it is 5 plus 2. So multiply 7 divided by 7.5 millimeter. So answer would be 1.87 multiplied 10 to the power of negative 4 Tesla. Okay. So next, going to explain the direction of movements of P and Q. So this is the same. So we know that we can use the Fleming left-hand rule to identify the direction of the force applied on the wire. So first of all, at wire P, so wire Q will apply magnetic field that is into the page. Okay, so and then you apply the Fleming left-hand rule, so it will be to the left. And the wire P also magnetic field, apply magnetic field on the wire Q is into the page. And if you apply the Fleming left-hand rule, you also obtain, the direction is to the right. So you can see that wire with different direction of current flow, they will experience repulsion force. That's what we have discussed before. So here, okay, so using Fleming left-hand rule, so the force applied on the P is to the left, while force on the Q is to the right. So it is a repulsion force that wire P will move to the left, while wire Q move to the right. So simple. So I proceed to question 17. Okay, a sinusoidal voltage we go to 240 sine 120 t. So we have a sine omega t. Okay, so we have angular frequency equal to 120. Okay, so remember omega is equal to 2 pi f. So if you need to find out the frequency, this is the formula. So the voltage is supplied to a circuit which consists of resistance 50 ohm and an inductor of inductance 0.2 Henry as shown in the diagram. Okay, so calculate the impedance. So impedance, we have the resistance and we have the reactance of the inductor. So first, we have the angular frequency as 120 that we'll use to calculate the reactance of inductor, which given as the formula of omega L. So omega 120 multiply the inductance 0.2 Henry, so that would be 24 ohm. Okay, so now we're going to calculate the impedance, which is the formula of square root of R squared, 50 squared, plus the reactance square. Okay, so which is 24 squared. Okay, so nothing much. So it is equal to 55.5 ohm. Okay, so next is to determine the maximum voltage across the inductor. So remember that this is a series circuit. A series circuit has the current as the constant variable. Okay, it is a ratio of voltage to the impedance, or the voltage of inductor to the reactance, or the voltage of the resistor to the resistance. So we don't have the voltage across the resistor. So maybe we can just use this formula that the applied voltage to the total impedance equal to the voltage across the inductor to the reactance. So if you rearrange this formula, so you will find something interesting that it is equal to XL over Z multiply V. Okay, so this is a formula that is similar to the potential divider. Okay, so put in the value. So we have the inductance over the total impedance 55.5 multiply the voltage. So we need to have the maximum voltage. So we can just use the peak voltage here. So if you need root mean square, you know what to do. So the maximum voltage across the inductor will be so 103.8. Okay, 103.8 watt. So next, calculate the phase angle and sketch a phasor diagram of the voltage supply and the current in the circuit. So simple. So phase angle, you should know we apply the trigonometry, shift tangent of the reactance to the resistance, or the voltage across the inductor to the voltage across the resistor. Okay. So we have the reactance. So we just apply reactance over the impedance, 55.5. It should be resistance, okay, which is 50. Okay, reactance over the resistance. Okay, so 24 divided by 50. So shift tangent. So we have the angle as 25.6 degree. So we also need to sketch a phasor diagram, so of the voltage supply and the current in the circuit. So I think if you remember, it will be good. So we know that the voltage across resistor as a reference point, and the current is in phase with the voltage across the resistance. Okay, so this is just a more complete diagram. So actually you can just draw the voltage supply and the current, but this is for the full illustration. So we know that the voltage across the inductor is leading by 90 degree. Okay, and then for the voltage supply, it will be the resultant vector here. And the angle that we have calculated, it is 25.6 degree. So in short, we can conclude that the voltage supply is leading the current by 25.6 degree. Okay. So we're going to enter section C. So two charged objects 12 centimeter apart repel each other with a force of 5 Newton. If the distance reduced to 4 centimeter, determine the force experienced by the two objects. So this is electrostatic, and it is about the force and the distance. So from the Coulomb's law, we learn about the force is inversely proportional to the square of the distance. Okay, so with this, we have the ratio of F1 over F2 equal to R2 square. Okay, so this is inversely proportional R1 square. So this is the formula that you can use. Okay, so you can calculate the full one, but I think we just apply the ratio here. So to calculate the force experienced by the two objects, so it will be equal to 12 centimeter divided by 3 centimeter. Okay, that will be square, don't forget, multiply 5 Newton. So this will, okay, sorry, this is 4. So this is 3 square times 5, that would be 45 Newton. Okay, so it should be no problem. So we proceed. B, a solid metal sphere with a radius of RA is located in the metal spherical shell with a radius of RB. solid metal sphere. Okay, solid metal sphere with a spherical shell. So something look like this. Okay. And we have the positive charge Q on the solid metal and negative charge on the surface of spherical. So I think this is quite obvious. Okay. So we didn't learn this in textbook, but we can do some analysis that positive and negative, they are attracted to one another. So electric field will be produced in between the metal sphere and the spherical shell. So this is what we have. So determine the electric potential for these two regions. So I think we learned about how to do the derivations. So the electric potential is defined as the work done to move a unit of positive charge from the infinity to a distance, okay, in the electric field. So if we continue to do the derivations, we have the force is force, work done is the force multiply the distance. So here is the integration that we can do. So force divided by Q, it will be the electric field strength. And electric field strength, we learned about the formula is Q over 4 pi r squared. So here I would add another region, which is R equal to RB for revision purpose. So let's try to do this. So we have a charge, okay, we are talking about the work done to move a charge from infinity to a point in the electric field. So far, if you move from the infinity to the point on the surface of spherical shell, I think there's no electric field that we have learned that there will be no work done. Okay, so integration of the EDR. Okay, so the electric potential. Okay, so the electric field strength is 0. So it means that the electric potential is 0. So it means that there is no work done to move the point charge, a unit positive charge from infinity to the surface of the spherical shell. So this is quite important if you want to proceed to the next condition. So now we're going to move the point charge between the region of the spherical shell and the metal sphere. Okay, so first we need to split into two conditions. First is from infinity to the spherical shell, and then from the spherical shell to any point between the two surfaces. Okay, so we need to have two things. So first is okay, of course, is from infinity, okay, to the surface RB. Okay, so since the electric field strength is 0, so it will be 0. Okay, and then we're going to plus from RB to any of the distance between RA and RB. So from RB to the R. Okay, so bear in mind that the force applied, okay, it is against the electric field. So you can see if you want to move it, okay, so the force and the electric field is in opposite directions. So before actually we move into this formula, actually we have like a prerequisite that something look like this. Okay, it is equal to, so this is the force, okay, and the force applied is in the opposite direction, so it will be a negative here. Okay, so this one you need to be careful. So apply the integration, so this would be cancelled out, and you have the V is equal to Q over 4 pi r. Okay, so from R to RB. Okay, so the rest is what you have learned is in max. So V is equal to Q over 4 pi r, okay, minus Q over 4 pi RB. Okay, so here we can see that RB is a constant value. Okay, and while the R Okay, it is a variable. Okay, it is any distance between RA and RB. So this is electric potential for the region between RA and RB. Okay, so next we're going to look for the third cases that now the point charge, we're going to move it into the metal sphere. Okay, into the metal sphere. So it is the same. So we still have, we need to split into three cases. So first is about the from infinity to RB, and then from RB to RA. Okay, from RB to RA, and then from RA to any of the distance that is less than the RA. Okay, from RA, move to any of the distance. Okay, so still zero, and also there's no magnetic field, electric field inside the metal sphere, as what we have learned before about the point charge or the spherical charge. Okay, so actually there is no electric field inside the metal sphere, so it will be zero in this case. Okay, so from here you just need to, I think everything is the same except the boundary condition is different compared to the previous solution. Okay, so what we have is we just repeat whatever we have, that we have this thing. Okay, so this should be one, this should be E, sorry. Okay. F. So this one it will be equal to the RA, okay, RB. Okay, so you just almost the same solution, except now you have Q over 4 pi RA minus Q over 4 pi RB. So here you can see that RA and RB is constant variable. Okay, they have constant value. So electric potential is the same inside the metal sphere. So if you want to plot the graph of the electric potential from the infinity to the point inside the metal sphere, so I think, okay, we have did it before. So from infinity to the point of RB, okay, it is zero, right? Okay, it is zero. Okay, it will be zero. And then the V in between the RB and RA, it is depending on the distance. Okay, so it will be equal to something like this. Okay, and then it will be constant in the region less than RA. Okay, so oh, sorry. Okay, so this is what you can imagine about the electric potential happening around these two charge object. So we proceed to the next question. If the metal spherical shell with the radius RB is removed, determine the electric field at any point outside the solid sphere using Gauss law. So this is quite straightforward. We have learned it before. So we remove the shell and we left with the metal sphere of RA. Okay, so we only need to derive for the electric field outside the solid sphere. So Gauss law is given as the total charge enclosed by the Gaussian surface divided by the permittivity of the medium. So this is by Gauss law, and we also have learned that the electric flux, it is given as the formula of EA. Okay. So we are going to derive the electric field. So we need to identify the suitable Gaussian surface, and it is the sphere that we have learned. So the area of a sphere is equal to 4 pi r squared. And then we just move the area to the side. Okay, it is electric field strength equal to Q over 4 pi epsilon r square, okay, which is the same as what we have learned. So this is applied to a sphere, charged spherical object. Okay, so 4 points, quite a lot. Okay, so proceed to the next question, C. So two oppositely charged horizontal plates of 1.3 centimeter apart have potential difference of 250 volt. An electron move into the region at equidistance. So equidistance, it means that the distance between the plate and the position, they are the same. So this is like the locus that we have learned, equidistant. So as shown in the diagram below, okay, so we can see that, okay, so determine the electric field between the plates. So I think this is quite straightforward. We have the formula of V over D. So the potential difference is 250 volt, 250 minus 0, divided by the distance between the plates, which is 1.3 centimeter. That would be 0.013 meter. So 250 divided by 0.013. So it is about 1.92 multiply 10 to the power 4. Okay, so electric field is watt per meter. Determine the work done for the electron to emerge at one end of the plate. Okay, so you want to emerge means escape. Okay, we need to reach to this point. Okay, so the work done. So it can be equal to the change in the electric potential energy. Okay, so it is means that we have the formula of QV. Or you can also use the formula of force multiply the distance, distance travel. So this solution actually has been discussed in one of my case study. So I'll put a link for you to look at it if you haven't looked so. So I think they are similar. So we proceed with the QV instead of FD because we need to calculate the force, so it will be extra works to do it. Okay, but it's quite worth to do study on it. So proceed with work done equal to QV. Okay, so the work done will be equal to the charge. So it is an electron. So electron charge multiply the potential difference. So bear in mind you are starting from the middle. So the electric field, electric potential between the two plates is linear. Okay, it means that if you have the graph, okay, the distance it is from 250 volt. Okay, it is going outward. It will be linearly decreasing up to 0, and the distance is 1.3 centimeter. Okay, so if you are in the middle, so it means it is half of the potential difference, which is 125 volt. So this is you are in a position that the electric potential is 125 volt. So to calculate the change in the electric potential energy, the potential difference would be equal to 250 minus 125 volt. So this is how we do the calculation for the work done. Okay, so electron charge, that would be constant of 23 multiply the potential difference, which is 125. So that will equal to 2 multiply 10 to the power of negative 17 joule. Okay, work done. Okay, so quite straightforward. So 5 marks. So if okay, we proceed to question 19 about the capacitor. So ABC is quite easy. It is what we have learned before in the lecture video. So here I just briefly go through. So define the capacitance of a capacitor. So it is the capability of capacitor to store charge, or technically it is the ratio of the charge on the capacitor to the potential difference across the capacitor with the formula of C equal to Q over V. Okay, 1 mark. So B, describe the mechanism of charging a parallel plate capacitor. So also what we have learned before, just you need to remember and explain it. Okay, so how is the charging process going? So first is when it is connected to a battery. So we learn about the electron is flowing out from the negative terminal. Okay, so it's an electron negative terminal to charge one of the plate to be negatively charged. Okay, and then it will induce a positive charge at another plate. So this process continues until the potential difference across the capacitor is equal to the EMF applied. Okay, so simple. So question C, what is the effect of capacitance if an insulating material, so you should know this is the dielectric, is inserted between the parallel plate capacitor? Explain how the effect happens. So also the same. So insulating material is also known as the dielectric. So when a capacitor is charged, electric field is produced between the positive and negative plate. So this will polarize the dielectric material, and the dielectric molecules will be aligned along the electric field where the positive end is attracted toward the negative plate and vice versa. So this will produce a reverse electric field that cause decrease in both resultant electric field strength and the potential difference between the capacitor plate. So it will reduce electric field, which the potential difference is depending on the electric field strength. Okay, V is equal to E over D. Okay, so from the formula of C equal to Q over V, so with the constant charge, the charge as the constant variable, when the voltage is decreased, the capacitance is increased. Okay, so this is how you can describe, okay, or explain the effect of the dielectric. So there's also case study about the dielectric. You can also watch back if you want to. So we'll proceed to question D. So a parallel plate of capacitor of area and charged by a battery of 6 volt. Separation between the plate is 10 millimeter. Space between the plate is filled by a mica with a dielectric constant of 5.4. So determine the capacitance of the capacitor. So capacitance is the formula we learned how to derive it. So if you don't remember, remember to derive. Okay, remember how you do the derivations. So it starts with the Gauss law. Okay, EA over Q over permittivity. Okay, so let us do revision on the derivation. So E is equal to V over D, okay, equal to Q over epsilon. So we need to get the capacitance, where the capacitance is known as the ratio of Q over V. So we need to have Q over V. So rearrange the equations. We can have Q over V, which is the capacitance. Okay. And that will be equal to, so you move V to here, and it will be epsilon permittivity multiply area divided by the distance between the plate. So yeah, so this is the formula. So if you don't remember, derivation is the key. Okay. So epsilon, so we can straight away apply the formula to solve question 1 to determine the capacitance of the capacitor. So we have the epsilon naught multiply the dielectric constant 5.4, multiply the area 144, change to meter square, that would be 10 to the power of -4, divided by the distance, which is the 10 millimeter or 0.01 meter. Okay, so do the calculation, shift constant of 32, multiply 5.4, multiply the area, divide by 0.01 meter. So that would be equal to 6.6 at 6 times 10 to the power of -11. So unit for capacitance, that would be farad. Okay. So we continue to second question, calculate the electric field between the plates. So simple. We have the battery as the potential difference divided by the separation distance. So 6 volt divided by the distance is 10 millimeter, 0.01 meter, and that will be equal to 600 watt per meter. Okay, so calculate the energy stored in the capacitor. So easy, half CV square. Or you can use other formula as well. So half times the capacitance. This is the one we have calculated. Multiply the voltage, which is 6 volt. So 6.86 multiply 36, 6 square, divided by 2. So that will be equal to 1.24 multiply 10 to the power of -9. So for energy, that will be joule. So proceed to the last question. Question 20. Describe a potential divider as a source of variable voltage. So there is a different answer for in the schema. So for me, I would use one of the example that I've discussed, which is the rheostat. So rheostat is also one of the example as serve as the potential divider. So if when you set out the circuit as shown in this diagram, okay, like what I've explained. So if you move the slider around, so you can change the resistance between point B and S. So which also affect the output voltage. Okay, so this is how we can use the rheostat to produce the variable voltage source. So the voltage is given as the resistance of Bs between B and S divided by the resistance of A and B between A and B, multiply the applied voltage. So this is how you use the rheostat as a source of variable voltage. Okay, so you can do more study about it, but this is a sample that I provide for you to study. So we continue to question B. Battery of 12 volts and a negligible internal resistance are connected to two resistors R1, R2, and RL as shown in the diagram below. So this question is quite simple, so I think not much problem here. So if the resistance of resistor R1, R2, RL is 5 ohm, 10 kilo ohm, and 5 kilo ohm, okay, respectively. So we are going to calculate output voltage across RL. Okay, so in SPM, we learn how to do it actually, but in Form 6, you learn how to use the potential divider, so which is much faster way to do it. So first, we need to find out the equivalent resistance between the parallel of 10 kilo ohm and the 5 kilo ohm. So just apply the formula and you will get 3.33 ohm. And to get the voltage output, so beside the method you use in SPM, we use potential divider in Form 6. So it will be equal to the resistance. Equivalent resistance is 3.33 divided by the total resistance, multiply the applied voltage, and you will get 4.8 volt. So this is for the first question. Second question, the current through each of the resistor. So simple as that. So for R1, okay, so I think we can just apply the voltage divided by the total resistance. Since the current flowing out from the battery is the same as the current through the R1. So I think we can just apply V equal to IR, 12 volts divided by the total resistance. That would be equal to 3.33 plus 5. Okay, so 12 divided by 8.33. So that will be equal to 1.44 milliampere. So be careful because this is a kilo ohm. So divided by kilo, you will get milliampere. And as for the current through R2, we also can apply V equal to IR. Then we know the voltage across these two resistors is 4.8 volt. So 4.8 divided by the resistance of R2, which is equal to 10 kilo ohm. Okay, 10 kilo ohm. So that will be equal to 0.48 milliampere. Okay, and for current through RL, so actually you also can apply the concept of the Kirchhoff current law, that the current here will be split. Okay, that will be split. Okay, so you know how to do it. Okay, so current you also can apply this method, that 1.44 minus 0.48. So that is equal to 0.96 milliampere. Okay, so you have many methods to do it. So this is just a rough discussion on how we can be flexible with the formula. Okay, so the third question, power dissipated at the load resistance. So you can use VI, V square over R, or I square R. Okay, it depends on you. So for me, I think I would just apply VI, where the voltage is 4.8 volt, multiply the current 0.96 milliampere. Okay, need to be careful. So 4.8 multiply 0.96 milliampere. So that will be equal to 4.61 milliwatt. Okay, 4.61 milliwatt. Okay. So need to be careful. Okay, so next potentiometer circuit consists of uniform slide wire XY, two cells with a negligible internal resistance E1 and E2, two identical resistor R, two switches S1, S2, and a galvanometer as shown in the diagram below. So the length of XY is 100 centimeter with resistance of 3 ohm if the EMF E1, E2, 2 volt and 1.3 volt respectively. Resistance of R is 0.5 ohm, so a lot of information have been given. Determine the balance length. So first of all, you need to understand what is balance length, okay, which what we have discussed before. So balance length is when the galvanometer reading is equal to 0, which means that the current between the J and this point is 0. There's no current flow between the top circuit, which is known as the driver circuit. Okay, there's no current flow from the top to the bottom. So this is the very important concept you need to understand for the potentiometer. So balance length is when there's no current. So what we have is that the voltage across X and J. Okay, this is what we have. Okay, the voltage across X and J is the same as what we have applied in the circuit below. Okay, so now we're going to look. Okay, the first case is both S1 and S2 are closed. So this is quite interesting that the switch is not connected in series in the circuit. Okay, like what we learned before is like it is in the series with the circuit, but now it is in parallel with the resistor. So this is something you need to be careful. Okay, when you close the switch, what happened? Okay, so the switch is something like you have a zero resistance. Okay, so when you close the switch, okay, so it's something like you are parallel with a zero resistance that will be equal to 0. Okay, because when you do the calculation, it will be 1 over R plus 1 over 0. Okay, so if you do the calculation, it will be 0 ohm. So this is something is very interesting. If you close the switch, you can ignore the resistance because the current will take a shortcut. Okay, so the current will flow. Okay, it will flow through the switch because it has zero resistance. Okay, because the resistor is a opposition to the current flow. So one with the opposition, one is with zero opposition. So current will definitely take the shortcut. So this is how the current behave when there is a path with a zero resistance. So from here, first case, both S1 and S2 are closed. So you can see we can just ignore these two R. So this would give us the circuit as shown in this diagram. Okay, so we're going to find the balance length so of xj. So without the internal resistance, so I think there is no internal resistance. So yeah, there is no internal resistance. Okay, so we just apply the concept of the potentiometer that the length is proportional to should be the voltage is proportional to the length of the wire. Okay, to the length of the wire. So we know that xy, okay, the voltage across xy is 2 volt. Okay, because the resistor here is ignored. Okay, it's short circuit. So all the voltage of 2 volt is applied on the wire xy. And we're going to find out the balance length, which representing the voltage of 1.3 volt. Okay, so we have the formula of V1 over V2 to the length 1 over length 2. Okay, so voltage, we're going to find the length, balance length of xj, okay, over the length of 100 centimeter. So that would reflect to the 1.3 volt divided by 2 volt. Okay, so 1.3 divided by 2 times 100. So that would give us 65 centimeter. Okay, so simple. So we're going to look at the next case. Both, S1 is open, S2 is closed. So S2 is closed means that we ignore this R, but now we need to take into account this resistance in this circuit because the S1 is open. So current need to go through the resistor. Okay, it cannot like because the half is closed. So we need to consider about the R on the top. So which give us the circuit of something like this. Okay. So the bottom is short circuit. So now we're going to revise again on the voltage. So first is the XY. Okay, so it's no longer 2 volt because you have a resistor here, 0.5 ohm that divide the voltage. Okay, divide portion of the voltage. So we need to revise again the voltage across the XY. So we just apply the potential divider where we are given with the resistance of wire XY is 3 ohm and the resistor R is 0.5 ohm. So 3 ohm over the total resistance, 3 plus 0.5 ohm, multiply the applied voltage, 2 volt. Okay, so 3 over 3.5 times 2. So this would give us 1.71 watt. Okay, so and then you just apply, okay, repeat the same things. So we do the ratio, except that the voltage between X and Y now is 1.71 watt. Okay, it is now 1.71 watt. So we are still looking for 1.3 watt because there is no resistor here. Okay, so 1.3 divided by 1.71 multiply 100. And this would give us 75.8 centimeter. So this would be the new length. Okay, so this is how we do the potentiometer, and this is the end of the past year 2019. So if you think the video is useful, do leave a like and subscribe me. So I will produce more video in future. See you again. Thank you for watching.